take a look at number 2. There's a lot of keywords in number 2. And without looking at a graph, which we will here in a second, without looking at a graph, I think there is one single word that indicates kind of where we're going with this and maybe some challenges that come ahead. Do you guys know what that one word is? Like when I see this word, I'm like, ooh, I think I might know what's going to happen. Regions is a close second.
Okay.
What's another keyword? So regions means more than one, right? No. Total area. Yeah. So because of that word total combined perhaps with that word regions, what this tells me is that there are going to be more than one region that we're going to have to consider. We're going to have to add up the areas of those different regions. And I think a graph is really, really helpful on this. So if you want to graph this on a calculator, of course, you're welcome to it. It's not too scary of a graph. I think it's just a parabola and a line. But having the calculator graph, the precision of that might be helpful. I will attempt to graph this off to the side. So let's see here, 2 minus x squared. You guys have something like that? Okay. So it does say the interval from -4 to 0. Is that what I want? Perhaps. Let's see here. This would be where having the calculator makes things a little bit easier or different than if you don't. So the key here for me is going to be, where is this, right? Where's that intersection point? That'll make all the difference. So if you've got the calculator, it's a pretty easy find to find the intersection point. If you don't, it's still pretty easy. What if I wanted to find where that is, but I didn't have a calculator? What would I have to do? Exactly. So it'd be 2 minus x squared is equal to x. So that would give me 0 equals x squared plus x minus 2. So 0 equals x plus 2, x minus 1. So I'm getting x equals -2, x equals +1. Sorry, that's off the screen there a little bit. But we got the most important part in there. Isn't that intersection point going to be where x equals -2? Okay. So if we really are trying to find the total area from -4 to 0, this kind of changes things a little bit. That means that my area, extend this down a little bit, my area would go from -4, which is out here, bless you, over here to 0. So for this part over here from -4 to -2, wouldn't the line be the high function? But then from -2 to 0, the parabola would be the high function. And so that's where we get that idea of total area of all the regions, more than one potentially, between these two graphs on that interval. That make sense? Okay. So because I've got two different regions, and depending on the region, either the line is higher or the parabola is higher, what does that lead us to do as far as a strategic path here? What are we going to have to do just kind of in general? Two different integrals, and then add it up, right? I agree. So for the red region, I think we'd go integral from -4 to -2. And since on that particular region the line is higher, we would go x minus 2 minus x squared dx. So if we correctly evaluate that, we would be finding the area of the red region. And then we would want to add to that the integral from -2 to 0. For the purple region, the parabola is the higher. So you'd go 2 minus x squared minus x dx. Okay, from a setup perspective, does that make sense? Okay, so remember it from the video or maybe from 8 months ago, the elements in there are actually really simple. Aren't the elements within the integrand simply height times base? We're doing little rectangles, and because of the integral being an infinite summation, we're squeezing the rectangles down to a 0 or towards a 0 width, with the height being varying depending on the different functions there. So it really is just base times height plus base times height, what it comes down to. Okay, so every now and then an AP question, almost for sure on an AP test, it'll happen at least one time. We're going to have to do something like that without the calculator. Okay, almost every time, something like that without the calculator. So take a minute and let's do it. Let's just practice it a little bit, go through all the details of the antiderivatives and FTC2 or 1 and all that stuff, and see if you can come to an agreement on what you think the answer would be. Rewrote it a little bit there, but when you do your antiderivatives, we would get 1/2 x squared minus 2x plus 1/3 x cubed, evaluated from -4 to -2 plus 2x minus 1/3 x cubed minus 1/2 x squared, evaluated from -2 to 0. Still good? So you do your FTC here, and it's going to be, I'm going to get rid of some of this. Do your FTC, and what in the world happens here? I'm going to do a little arithmetic in my head. So if you plug in the -2, you should get 2 plus 4 minus 8/3 minus, if you plug in the -4, you should get 8 plus 8 minus 64/3. So pardon the arithmetic step skipping. Is that okay? All right, and then plus, thankfully, that's kind of nice. Plug in the 0. What do you get? 0. Yay. Okay, so then minus, plugging in the -2, we will get -4 plus 8/3 minus 2. And like Caroline and I were just talking about, if this were an FRQ, why on earth would you go anywhere past that? You better not, right? Seriously, like it's all risk and no reward. Like if you execute it correctly and go all the way through the end, you get no more points than if you just left it like that. We're talking about on the AP FRQ stuff, right? But that being a correct answer, I think, if you did keep on going, trying to simplify it all the way down, you made one little itty bitty mistake, you would lose the point that you just gained right there. So just keep that in mind. Obviously, we're talking about way in the future, but from an AP FRQ perspective, you should just stop right there. Okay, anyway, I will keep going, though. I will take the risk because we're all together here, right? We can do this. So I get, let's see here, 6 minus 8/3 right there. And then, so it'd be minus 16 plus 64/3 plus 4 minus 8/3 plus 2. So, golly, how does this end up working out? So, Okay, so that's -4. So it'd be -4 minus 16/3 plus 64/3. So let's see here, that would be 48/3, which is 16 plus -4 is 12. And I saw that 12 on a couple of papers. So yeah, so kind of a long journey to end up there. If you got there, nice job. Keeping track of all those fractions and other various numbers and things. Definitely a hefty thing to do, especially in the context of a quiz or a test. Get it? So, be smart when it comes to that. Do you guys have any questions at all? Okay. All right, let's take a look at our next one. The next one is a little different. It is a twist, if you will. So I prefaced this by saying sometimes it's easier to use a horizontal representative rectangle. And I literally mean that. Sometimes it is and sometimes it isn't. It's going to be based on the nature of the shape, and I'll try to explain what factors would influence you towards this or away from this. So when you do this, and this could happen at any point, the representative rectangle is no longer expressed in the same terms as far as the width. So previously, like in the question we just did, the width or the base length was dx. So if you take a representative rectangle and make it a horizontal length, then now the base has been kind of twisted over and it's no longer dx, now it's dy. So it's dy wide or dy thick. And because of this, everything within your integral, your integrand, your limits, everything will have to be in terms of y. So I'll just have to be y's. So most folks get the integrand part. Some people will forget the limits, from 2 to 7 or whatever. Those have to be in terms of y as well. In cases like this, if we're talking about horizontal relationship as opposed to a vertical relationship, which function would be the one that's higher, like the one that comes first in the integrand? We'll come back to that. Okay, fair enough. Let's graph number 3, and then we'll answer the what is the higher function question. So what do you notice first about these? Yeah, they're not y equals. They're not written in function form at all, right? They're x is the dependent and y is the independent. So I'm hoping that I know we did this a little bit last year, and at the most on the AP test there's probably one of these. Hopefully that you did this in a pre-calc class where you can graph these where essentially the x and the y axes are exchanged, more or less. So if you want to look at the graph here, the first graph, x equals 3 minus y squared, how would you describe the shape of the graph? Sideways parabola would be a good description. I agree. Which way does it open? Since it's sideways, does the parabola open left or right? It opens to the left, yes. And that's because it's minus y squared. And then it's been shifted, right? The 3 is going to move it. Which way is the 3 going to move it? To the right. Yep. So ups and downs, lefts and rights have all been exchanged, essentially. So this parabola would look like roughly like that. Okay, and then what's the other graph? How would you describe the shape of that graph? It's a line. I agree. And I would say graphing this line, it might actually be easier to put it in the kind of the typical slope-intercept form. So if we subtracted 1 over x minus 1, yeah, so a y-intercept of -1 with a slope of 1. It's the same graph, just written a little bit differently. So something like that. Okay, so let's talk a little bit about the strategy that we will take and why we're going to do this. So can you see the region, by the way? I don't know if I can, I'll try to highlight it a little bit here. That make sense? That region right there? Okay, so can I convince you of why we're going to use y instead of x? So if we were going to use x, if we're going to use dx's, then we'd be using vertical representative rectangles, which would look something like this. Right, that'd be a dx wide representative rectangle, and that would be fine. It's totally fine. So if we accumulate these representative rectangles starting over here, and we work our way from left to right, all the way across here, all these little representative rectangles would be great. The high function is the line, the low function is the parabola, and accepting the fact that you'd have to, solve for y on the parabola, this wouldn't be too bad. But then once you get over here to this region, no longer is the top determined by the line and the bottom by the parabola. Now the top and bottom are both determined by the parabola. And all of this would be doable. It's just that you're going to have to split your integrand up into two separate integrals and consider, okay, the symmetry of this, and what about the plus or minus on the square root when I square root both sides? It's going to be rough, right? Instead of doing that, what I would suggest we do, and draw the picture like this, is use a horizontal representative rectangle, which is dy thick. And the nice thing about this is no matter where you draw the representative rectangle in, the left side is determined by the line, and the right side is determined by the parabola. And so there will be no algebra gymnastics with trying to solve for this or solve for that, or calculus gymnastics of splitting the integrand up into two different integrals and all that stuff. This just makes it a one process thing instead of multiple processes and trying to put them back together again. The other way is doable. I'm not telling you can't do it that way. I'm just saying this way is better. So if you would, answer that question, and then I'll let you guys try it. It says, in a cases like this, what would be the higher function? Like which one would come first in your integrand?
3 minus y squared.
Because it's on the right. Yeah, so the right side would be like your high side. Left side would be your low side. Okay, so give it a shot. So I'll try that. So I don't know, where do we start? We need to set up our integral. We are missing a couple of key pieces of information at this point. So I'm going to say integral, and maybe the first thought is, awesome, integral, from where to where? We got to think about that one for a second. Yeah, the intersection points are going to be key here. So let's find those intersection points. And I don't know if you did this via calculator or if you did it by hand. It's doable either way, I would imagine. What did you guys come up with for the intersection stop? There we go. Intersection points there.
-2 and 1.
So negative 2 comma 1? Which that can't be a positive one.
Not that one.
Yeah, but is it x equals negative 2 or y equals negative? Like, do you see what I'm getting at?
Yeah.
Like, what are the actual coordinates?
Oh, over there.
Something comma something. I honestly, we can figure it out. I'll try it. So
It's a y equals -2.
y equal, okay, so it's right there is negative 2. So if that's negative 2, then it would have to be negative 1, wouldn't it? Or no, that's a y equals negative 2? Sorry. Negative 2 right there, so then x would have to be negative 1. Am I correct? It's got to be. Okay, then up there is what? 2 comma 1? Okay. Some degree of symmetry there. You guys all okay with that? You could set them equal to each other and solve. You could use a calculator if the calculator is active. A number of ways you could do that. The calculator would be tough because you'd have to solve for y. It wouldn't be the easiest thing, but it wouldn't be that bad either. So when I set up my integral, there it is. What's going to be the low value of my integration? Like I'm going to start and stop where? Okay, so negative 2, and we're going to end up where? Negative 2 to 1. Let's analyze that real quick. When you have a vertical representative rectangle, so not like this. You have a vertical representative rectangle, don't you accumulate from left to right? But when you have horizontal representative rectangles, we accumulate from bottom to top. And so we're going to be accumulating from here up to here. And so that's why we've got to have those y values, because the y's are what describe bottom to top, not the x's. And so I do agree with the idea of integrating from y equals negative 2 up to y equals 1, simply where we're going to start accumulating and where we're going to stop accumulating. Okay, and then the right minus left concept would be 3 minus y squared minus the quantity of y plus 1. And then the width is dy. So once you get to that point, that is your complete integrand. It is, like before, length times width on a rectangle. You okay? Okay. Okay. So then as far as working out the details here, this would be the integral from -2 to 1, and it would be, what, 2 minus y squared? I think if we simplify that, yeah. And then we just follow our steps to evaluate it. We find our antiderivative first, so that would be 2y minus 1/2 y squared minus 1/3 y cubed, evaluated from -2 to 1. And let's see how this works. I'm getting 2 minus 1/2 minus 1/3 minus, when we evaluate at -2, I'm getting -4 minus 2 plus 8/3. And once again, if this was an FRQ and you go past this, you're taking a risk that you probably shouldn't be taking. But let's keep going since it's not the AP test. Goodness, what's going to be the easiest way to do this? So if I handle all my fractions and non-fractions separately, it's going to be 2 minus -6. So that's going to give me 8. And with my fractions, let's see here, -1/2 minus 1/3 is -5/6. -5/6 minus 8/3. So that's minus 21/6, right? So I'm getting this. It is Monday morning. So that would be 48/6 minus 21/6, which is 27/6, which reduces to 9/2, right? You guys get the same thing? 4.5? Okay, so all of those final couple of arithmetic steps are entirely unnecessary on an AP test. But again, good practice. You guys get it okay? Awesome. Final example of the morning is right here. Number 4. Definitely calculator active here to help you kind of see the connection between the graphs. So go ahead and do that with your calculators and just kind of see what this looks like, graphically speaking. Bunch of stuff going on. You got a piecewise, and then 2 other boundaries for this. I will try to sketch it out myself. So I'm really grateful that the calculator is active here. This will make the finish of this quite a bit easier. Graph-wise, does this make sense? See it okay? The purple graph is supposed to be the 2e to the x, which would then be continuous, not differentiable necessarily, but continuous with the parabola there when x is 0. We'd have continuity there. The parabola is the red graph. The blue line is the y equals -x graph. X equals 1 is vertical. That's the brown line off to the right. Okay. Okay, so I'll give you guys a couple minutes to do this. Our class ends at 9:30, right? Yes. Okay, so we got a few minutes. So basically, since the calculator is active here, you want to set this up and then probably just use Math 9 to complete the evaluation. I'll give you guys for maybe like 3 minutes or so to at least get it set up. And I'll get the setup on here, and then hopefully we can agree on an approximate answer as well. To you guys here. Representative rectangle for this being vertical, you're going to have a representative rectangle over here on this little piece on the left. Then you're going to have a representative rectangle on the right that's determined by different circumstances. And so we need 2 separate integrands. So for the first one, we're going to integrate from something to 0, right? Wouldn't it be intersection point to 0? So what would that intersection point on the left have to be? (8526055) Okay. And then over there, the high function is the exponential. So it would be 2e to the x minus the low function would be that blue line, so minus negative x dx. And then we'd need to add to that the integral from 0 to 1 to get us all the way over to the brown line. But this time the high function is no longer the exponential, now it's the parabola. So that would be x squared plus 2 minus the low function being, again, the line, negative x dx. So that's a good setup. Now you got to use Math 9. Did you guys do it? Let's hear what you got. 3.6173. Do you guys all agree with that? So hopefully if Lenny and Darian are watching this, they'll agree with that number as well. So, fantastic. You guys are doing well. Not surprised.